so let me first tell what the digital twin is. So if we look at the original regarding our original definition, a ship digital twin has to have two distinct things to be counted as a digital twin. And these are quite new, by the way. The fathers of of the digital twin concept have established these, of course, and they are quite new, as I said. The first one is a paper back in 2017, and the second is 2018. Actually, this digital twin concept is about 25 years old, but the clear definitions are quite new. The first thing that we have to keep in mind is if a ship is a digital, if any object has a digital twin, that digital twin should be able to operate independently, should have the capability to operate independently. And the second is it must support bidirectional data exchange. So if we think of, for instance, digital models are able to operate independently, but they have no physical connectivity with the real world. So there's no bidirectional data exchange. So digital models are not digital twins. Digital shadows, in the meanwhile, they are not able to operate. I mean, it violates the first rule. They are not able to operate independently. A ship digital shadow only follows what is being done in the in the physical ship. I mean, it's not a standalone entity. Yes, and also there's no bidirectional data exchange. There's only one-way flow of data from the physical to the virtual. There's no flow of data from the virtual world to the physical world. Okay, so reminding these two prerequisites for ship digital twin, we could continue. A digital twin involves a two-way data exchange between a physical object and a computer. While it uses sensors like a digital shadow, it also has a control algorithm. This algorithm processes the sensor data and automatically sends commands back to the physical ship to control its equipment, like or actuators, like the propeller, the rudder, or the thrusters, bow thrusters, stern thrusters, any actuator it might have. In digital twin, I mean, if we're talking about ship navigation autonomy, and if we have to have a bidirectional data exchange, then there has to be a control algorithm. A digital twin is a virtual copy that mirrors a physical system and stays linked to it for its life. For ship navigation, this computer model that simulates the ship's motion. I mean, if there's a bidirectional data exchange, then there has to be a controller inside that computer, so it could provide feedback from the virtual world to the physical world. In a ship digital twin, real sensor data is fused with a high-quality virtual model or high-fidelity kinematic models. A control algorithm then uses this combined information to generate commands that guide the ship to its desired state. Ultimately, the physical ship is now controlled and influenced by its virtual counterpart, which was missing in digital shadow. In digital shadow, we were only receiving feedback of what is being happened in the physical world, but we didn't provide any data back to from the virtual world back to the physical ship. So that was only one-way data exchange. Here we have bidirectional, two-way data exchange. Again, there are two progressive levels here. The first level of SDT, ship digital twin, is automated advisory system. Bidirectional loop is established here, and the level 1 SDT acts as a real-time advisory or automated remote control. To achieve SDT level 2, ship digital twin level 2, we have to integrate artificial intelligence or machine learning algorithms for self-correction, and it will fully replace human in the loop. Let me explain these to you. The first level is at the left-hand side. The second level is at the right-hand side. Ship Digital Level 1 introduces a high-fidelity digital twin architecture that supports automated decision-making capabilities. You see there are lots of arrows here, so things are getting a bit more complicated. The architecture integrates key physical phenomena, including hydrodynamic forces, actuator response plays, and environmental disturbances such as waves, currents, and wind. The kinematic model is also integrated to the sensor fusion filters. Here you see a kinematic model, and it feeds the sensor fusion filters. I mean, you see the arrow coming from sensors here, and it's also fed by the high fidelity kinematic model because of you have to filter out the noise induced by the sensors, and that is being done by high fidelity kinematic models. And the data produced here goes back to the controller, you see, and also to the decision algorithm. The kinematic model is also integrated into the sensor fusion filters to improve the accuracy of the ship state estimations, thereby enhancing the performance of both the decision algorithm, you see here, and the controller, you see the two arrows. At Ship Digital Twin Level 2, it's also, I mean, it's nearly the same. The decision-making architecture advances significantly with the integration of artificial intelligence and machine learning. Here we have an AI and ML model in the decision algorithm process. A core component of this level is the machine learning model initially trained using high-fidelity kinematic simulations. In our Ship Digital Twin Level 2 setup, the kinematic model plays two key roles. First, it supports sensor fusion algorithms by serving as a reference model, helping to detect and correct outlier measurements. You see, this is given by the first arrow here. And the second aim is it acts as the training environment for the AI agent during its reinforcement learning process. You see, there's an arrow going back to the AI ML process. So AI ML models are not born with zero knowledge. They are first trained with high fidelity kinematic models in the highest degree. Then when the ship starts operating, the decision algorithm, you place the AI ML model in the decision algorithm, it's born with it. Then it collects data, and in the meanwhile, this AI ML model is still being trained with the real data flown from the physical ship. First stage is in the digital world training. The actual training is in the physical. The first training is in the virtual world. The second training and the best training is in the physical world. And this is the highest level in Ship Digital Twin, which is level 2. This system, this setup has two key benefits. It makes the system more robust by checking real data against a reliable simulation. It also allows for continuous learning as the AI is refined using data collected from the ship and its surroundings. As a result, the ship's decision-making gets better and better and more capable with every voyage, which is a process we call the growth of maritime intelligence or maritime intelligence maturation. So it gets matured as it gets older, like humans do.